In this video, we're going to derive where the formulas for the slope and concavity of a point along a parametric curve comes from. And as a spoiler, this is going to be a lot of chain rule differentiation from how we thought about this from Calc A, working from the outside and differentiating our way inside of a function. So let's just remember how the chain rule works. So first let's consider this function y that's a function of x, and it's equal to 1 plus x to the power of 3. If we differentiate this, dy dx, so this is not a parametric curve, this is just a function like we thought of from Calc A. We would bring that 3 down in front using the differentiation power rule. And then we have 1 plus x raised to that power minus 1. So we get 3 minus 1 or to a power 2. And now if we wanted to keep going, of course, we would have to differentiate the inside of that parenthesis term, 1 plus x. It just so happens that in this case, that is equal to 1. So this derivative at the end of the day is 3 times 1 plus x raised to the power 2. You might be wondering, well, why or where am I going with this? Well, let's consider a slightly different function now, where our function y is a function of t, although the function y itself looks very similar to the previous function. We have 1 plus t cubed instead of a 1 plus x, and all that raised to the power of 3. So in this particular problem, this t cubed looks just like it's in that same place as the x in the previous. In fact, we could view this as x is equal to t cubed in this case. And if we actually view it in this kind of idea, we can write the function y in the following way. We actually have y is equal to y, which itself is a function of x, where x itself is a function of t. So if we did that, you might be wondering, wait, why actually would we do that? Well, let's actually come back to that in a moment. Let's first try to take the derivative of this above function, dy dt. And if we take the derivative of this function, a lot of the same steps will be there. For example, this 3 will come down in front. We'll get a 1 plus whatever's inside that, which in this case is a 1 plus t cubed, raised to the power 2. And then we multiply by the derivative of what's inside. In the previous problem, the derivative of what's inside was just 1. In this case, the derivative of what's inside is a 3t squared for the derivative of the 1 plus t cubed with respect to t. Now, why is this actually somewhat interesting or somewhat informative for us? Well, the derivatives look very similar, at least the first part, except, of course, in the second case, we have that t cubed. But if we called that t cubed x, the first part of that derivative would be the same. The difference, of course, is the second part, the 3t squared versus the 1. So actually, if we think about this 3t squared term, what that actually looks like is if we let x equal t cubed, that would actually be equal to dx dt. And the reason, or where I'm going with this, is we're going to be able to see that our function or our derivative for this chain rule operation can be written in the following way, using sort of that onion idea of differentiating from the outside and continually moving on the inside. So thinking about this second case now, ultimately we're finding a derivative of y with respect to t, because again, our function y is ultimately a function of t after all of those compositions of functions. So dy dt is equal to, moving on the outside in, if we did call that t cubed x, so instead of having t cubed, if we really just called this first thing x and then defined x as t cubed itself, this first term in blue that I highlighted, that whole derivative there is actually dy dx in the very similar way to how we computed that before. And then this last derivative was dx dt. And now you can notice that this chain rule thing, if we look at the right-hand side and we crossed out those dx's, it looks like we'd just be left with dy dt, which would match up with what we have on the left-hand side. So this is how chain rule ultimately works, even though we might at this point just be so used to kind of differentiating on the outside in. And what I want to draw our attention to right now is this slope. We have dy dx, change in y over change in x type quantity. This is what we want to actually solve for our parametric curve. So if we actually go ahead and solve for that quantity, we will get dy dx is equal to, well, dy dt all over dx dt. So this is where the slope formula actually comes from parametric curves. It really comes from chain rule differentiation. Again, I want to emphasize, if we're computing the slope along a parametric curve, we would take the derivative of the y equation with respect to the parameter, the derivative of the x equation with respect to the parameter, divide the y derivative by the x derivative, and that gives us the overall slope formula for that parametric curve. That right-hand side will be a function of that parameter. Now, the second derivative for concavity works out slightly differently, but we're going to bring our friend that we just found, that dy dx, back to the mix. And what I want us to emphasize here is we're going to view this as what we call a mathematical operator. So dy dx, I can rewrite in the following way, and please just hold with me for a few seconds here. So I'm going to write that derivative, or 1 over dx dt first, times dy dt. So again, this is mathematically equivalent to the previous thing. I'm just writing that first kind of 1 over that dx dt term. And I want us to recognize the following. On the left side, I have this y. On the right side, I also have this y sitting there. And basically, I'm going to look at this in the following way. I'm going to surround that y with open parentheses. The reason why here is, in a moment, I'm just going to get rid of that y altogether. And this kind of might feel similar to when we did the composition of functions or stenciling with power series and Taylor series. So for example, if I just rewrite that down below, what I really have is, on that left-hand side, the derivative with respect to x of whatever I put in those parentheses is equal to 1 over dx dt times the derivative with respect to t of whatever I put in those parentheses. So what I want us to emphasize here is, this gives us a method for computing derivatives with respect to x, even though we have a parametric curve. And the reason why we might want this is this left-hand side in a moment, if we just put in the derivative dy dx into there, what this left-hand side overall gives us is the second derivative, or the concavity. The second derivative of y with respect to x. So if we just put that on the right-hand side, we have a formula now for computing the concavity at any point along a parametric curve. So we have this sort of differentiation operator, just like we saw kind of with power series, Taylor series, and did the composition of functions and stenciling there. So at the end of the day, our second derivative, or the way we can compute concavity, is the following. The second derivative of y with respect to x is equal to 1 over the derivative of x with respect to the parameter times the derivative with respect to t of whatever our first derivative was. So that first derivative, dy dx, or the slope, remember, is a function of that parameter, just like we talked about a few moments ago. So let's actually go ahead and do some examples of this. So I'm going to circle this because this is actually our formula for computing concavity. But let's actually just compute the slope and the concavity in general for a parametric curve. So let's say x of t, our parametric curve, is defined by, let's go with 5 minus t squared, and y of t is equal to, let's go with 2t plus t cubed. So the first thing we'll compute is the slope. So if we go back a couple moments, we'll see that our slope formula is the change in y over change in x, again, rise over run, is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. So as long as we can compute those individual coordinate derivatives, we can plug them in the appropriate way. So dy dx is equal to, well, the derivative first, let's take the derivative of y with respect to t. Taking that derivative will give us a 2 plus 3t squared in the numerator. Now, the dx dt in that denominator, we take the derivative of the x equation, which in this case will give us a minus 2t. All right, so that is how we can compute the slope for a parametric curve, derivative of the y equation, or the y coordinate with respect to the parameter, divided by the x coordinates derivative with respect to the parameter. We can just do a little simplification here, actually. So this first, since we have one term in the denominator, we can divide that into both terms in the numerator. So we have a 2 divided by negative 2t, and then we have a minus 3t squared all over 2t. So at the end of the day, our slope equation looks like the following. Dy dx is equal to a minus 1 over t minus 3t over 2, or 3 halves times t. So that's our first derivative, or sorry, our slope of our parametric curve. So let's go ahead and try to find the concavity. And a few things to note, remember, this slope equation, that right-hand side is a function of the parameter, t. So let's go ahead and remind ourselves what that concavity formula was up above. So the concavity formula, the second derivative of y with respect to x, is equal to 1 over the x coordinates derivative with respect to the parameter times the derivative of the slope that we computed with respect to t, the parameter. So let me just write that formula down below as well. And again, if we look through this, there's a couple things we've already computed, like we computed dx dt before because we needed that for the slope. And then the other thing we'll need to compute is the derivative with respect to t of our slope. And again, that makes sense because this slope is a function of our parameter t. So let's just plug in things that we know now. The first thing, let's go ahead and remind ourselves, Well, we need to divide by the derivative of x with respect to the parameter, which was taking our x equation and taking its derivative with respect to t, which in this case is a minus 2t. So we get 1 over minus 2t. Next, we're taking the derivative with respect to t of our slope equation or slope formula, dy dx, which we're going to take our slope that we computed up above and plug it in. So we take a derivative with respect to t of minus 1 over t minus 3/2 times t. So this first term is a minus 1 over 2t. We're taking a derivative of that second term now. I'm just going to rewrite that first term to make this a little easier for us to do the differentiation power rule. So we can write that as a minus t to the minus 1. And that second term we can just leave as 3/2 times t. Of course, well, that's t to the first. So let's just roll through with this derivative with respect to t then. First term again stays the same. That's 1 over dx dt. dx dt was 2t. We just leave that the same. Now taking a derivative of this second piece. The first thing is, well, we do the the differentiation power rule. So differentiating that minus t to the minus 1, that minus 1 will come down. So we have minus 1 times minus 1 gives us a plus 1. So we have a plus 1t to the minus 2 power. And then the second term, when we differentiate the 3/2 t to the first, that'll just give us a 3/2. And this is our formula for the concavity at any point along that parametric curve that we were given.